Hey guys, my name is Hiraku Murakami. I'm here with NovaEdge Academics, and today we'll be going over Topic A1 Kinematics Part 1. So first, we're going to start off with the difference between scalar and vector quantities. In the universe, we have a bunch of quantities that we allocate them to either scalar or vector. As an example, a distance is a scalar quantity. So what do we mean by scalar and vector quantity? Well, they both have magnitude. And what do we mean by magnitude? Well, let's say the park from my house is 30 meters away. Well, that 30 is the magnitude of the quantity. Well, vector differs from scalar quantities in one way, and that is that it has a direction. Scalar quantities do not have a direction. And what do we mean by this? Well, for example, right, if I say that I have 2 eggs, right, for me to possess 2 eggs, there is no sense of direction. I just have 2 eggs, right? So 2 here in this case is the magnitude, and thus it is a scalar quantity because I can't have 2 eggs in the right or left direction, right? I can just have 2 eggs. But as an example for a vector, right, I could like push something to the right or left, right? I could push a box forward, for example, or I could pull a box backwards, right? And this pushing pulling motion, we call it force. So force is a vector quantity. So I can push at a certain strength towards someone, right? To the right, to the left. So it has a sense of direction. Therefore, it is considered a vector. We're going to talk more about it in the next slide in detail, but some other quantities of scalar quantities are speed, mass, and time. So you can notice that these do not have a sense of direction. Whereas for vector quantities, we have displacement, velocity, acceleration, force, and later chapters are going to cover things like momentum. Okay. First, let's talk about the difference between distance and displacement. Well, distance is defined as the total movement of an object regardless of the direction. Okay, this is quite simple. It's something we use in a day-to-day basis. However, the one that we care about, the direction, is called displacement. Okay, and that is a net change in position. So as an example here, if I go on a walk on let's say a little trail, and this distance is, let's say, 500 meters, right? That's how much I walked, right? So I don't care where I'm going. I'm closing my eyes and I'm tracking how many steps I'm taking. Turns out that is 500 meters, right? However, if I compare from position A to position B, it turns out that from position A to B, there is 50 meters apart. They are 50 meters apart. And that's what we call displacement. And the displacement, the direction matters. You can see how there is an arrow here, right? I'm saying that I displaced myself from point A to B 50 meters in a southeast direction, right? For a distance, I don't care where I'm going. As I walk, I could turn right, I could turn left. The distance does not change. However, the displacement does, okay? Now, this is true for any vector quantities, but vector quantities can be positive or negative. And what does that mean, right? How can you have a negative quantity, right? Well, the negative and positive, they indicate the direction of the quantity. So as an example, in the scenario A, we have 0 displacement, right? The ball is just staying at 0. In position B, we have a displacement of plus 3 meters, okay? What do we mean by plus? It means it went to the right. Okay, and so positive values are used for going to the right or going up, whereas negative can be used for going to the left or going down. So as an example, in scenario C, we have negative 4 meters of displacement. Okay, so the positive and negative is really, really important. Now, another example is speed versus velocity. We define speed as the distance covered over time. However, velocity is a vector form, and it is the displacement over time. So if we use the same scenario where this one was 500 meters and the displacement was 50 meters, if I say that I took 10 seconds to get from position A to position B, my speed is equal to 500 meters divided by 10 seconds, and that is 50 meters per second. However, my velocity is equal to 50 meters divided by 10 seconds, and that is plus 5 meters per second. And I'm putting plus as, you know, we have southeast right now. I'm just considering it as a plus value for now. So my velocity is plus 5 meters per second, but my speed is 50 meters per second. Now, your speed will always be greater or equal to the velocity. There is no way that velocity is greater than the speed. Just keep that in mind. Now let's talk about acceleration. Well, acceleration is a change in velocity over time. Okay, so for us, we define acceleration as v minus u over t. What does v mean? That's the final velocity. And what does u mean? That's the initial velocity. And why do we care about this? Well, if I want to measure a change in something, I need to measure the final value minus the initial value. So in this case, it's a final velocity minus the initial velocity divided by time. And that's what we define as acceleration. Now, we also have something called deceleration. And deceleration just means slowing down. But in this case, the acceleration is actually a negative value. So keep that in mind. So if it's a positive value, it is always speeding up, even if it's from like 0.5 meters per second squared. That is still accelerating. The velocity is still going up, right? However, deceleration is a negative value, meaning velocity is going down, okay? So let's do a practice problem. Pause the video and try this on your own. And now I'm going to cover it. So part A. So the car is already moving at 12.5 meters, which means this is the u value. And this is the acceleration, 0.85. So if I rearrange this formula to isolate v, the final velocity, I can solve for this. So I'm going to multiply both sides by t, and then add both sides by u to isolate v, and that's going to be equal to this is equal to 16.41. Make sure you put the significant figure. I'll cover in another video what that means, but that is 16.4 meters per second. So part B, well, for me to get to 5 meters per second as a final value in 12 seconds, my initial velocity in this case is the 16.4 meters per second, right? So acceleration is equal to the final minus initial divided by t. So final is 5, initial is 16.4, divided by 12. And you should get negative 0.95 meters per second squared. Okay, let's move on to graphs interpretation. So in the IB Physics, this is a completely unnecessary skill to be able to interpret graphs properly and extract the appropriate information out of this. It is especially essential in paper 1 problems, down the road in any other topic as well. So let's use this as an example. So two things that matter in the graphs are, well, first we have the y and x axis, right? So y and x axis. And the two things that are important are slope and the area under the curve. So here I wrote gradient and area under the curve. Gradient is just delta y over delta x. And the area is delta y times delta x. So two different things. One is division and one is multiplication, right? Area is always multiplication. If I have a rectangle and I call this AB, then the area is equal to A times B, right? So it's a multiplication, right? Slope is division. So how do I interpret data and extract something out of it? Well, if I want to draw the velocity time graph, I know that velocity is equal to displacement over time, right? Now, do you see this looks like this? What I'm saying here is that velocity is the slope of s versus t time graph. It is the slope of it. So if I were to measure the slope, let's say at the beginning I have 0, then I have 0 velocity. In the midpoint, let's say I have a slope of 2, then at the same time, this point, my velocity is 2, okay? And I can keep doing that for the third one, let's say here at the end. I'm going to say that the slope here is equal to 4, let's say. So at time equals here, I have a slope of 4, okay? And if I were to, oh, that's a bit wrong, somewhere maybe here. And if I were to draw a line, it would be maybe something like that, okay? I'm going to move this up here, okay? So that's how I can find the velocity time graph, is extracting information out of distance time graph and bringing it to the velocity. Now, interesting thing, I can do the same thing for acceleration, because acceleration is now delta v over delta t. And you can see that's the slope of the velocity time graph that we have, okay? And luckily for this, for a simplistic reason, the slope is uniform, and the slope, let's just call it 2, for example. Then in the acceleration, I can have a uniform acceleration. So velocity is always increasing, right? But at the constant rate of 2 meters per second squared. That is the acceleration here, okay? Extremely important. So let's do an example. I'm going to give you the velocity time graph, and I want you to pause the video and try to draw the acceleration time graph and displacement time graph. So I'm going to give you the answer now. Okay, so first let's start from acceleration time graph. I already know this is the delta v over delta t, that's the slope. The slope of this graph is 0, right? It's always 0. So my answer is going to be actually 0 at the bottom. Quite easy, right? So it was a trick question, okay? Now how about I want to draw the displacement time graph in this case, right? So I want to extract information from this graph and draw this graph. How do I do that? Well, I actually need to use the area under the curve, and I'll tell you why. Well, I know that velocity is equal to delta s over delta t. If I were to multiply both sides, I get delta v, or v times delta t is equal to delta s. Okay, now this is the area. It's the multiplication. We did this already, right? It's the delta y times delta x that I wrote here. Okay, so when I try to find the area under the curve, I can actually find the displacement at that time. So let's find it. Well, at t equals 1, I have area is 5. So I have 5 here. At t equals 2, the area under the curve is 10. So I have 10 here. At t equals 3, I have 15. So I have 15 here. And all I need to do is draw a line connecting the dots. And I should get a straight line like this. So there you go. So let's do a textbook problem. Pause the video and take a look and try and do this yourself. I'm going to give you the answer in a second. Alright, so part A. Describe the straight line motion represented by the graph. In the first section, let's call this I. The velocity is increasing at a uniform rate. That means acceleration is positive. In part I, acceleration is 0 because velocity is constant. Part 3, well, the velocity is decreasing at a uniform rate, which means acceleration is negative, okay? Part B, calculate the accelerations. Acceleration is delta v over delta t. It's the slope. So in part I have 3 over 2. Part 2, I have 0. In part 3, I have negative 3 over 1 meters per second squared, okay? Part C, what was the total distance traveled? The distance traveled is the area under the curve, right? So let's get the area under the curve. The area under the curve is 3 times 2 divided by 2. So in part A, part 1 is 3 times 2 divided by 2, which is 3. Part 2, that is the area of this part, which is 4 by 3 rectangle, 4 times 3. And part 3, that is just 3 divided by 2, that is 1.5 meters. Okay, meters for all of them. Cool. Part D, what was the average velocity? Well, we can get the average velocity because we know the total distance traveled and the total time it took to travel that distance. So velocity is equal to s over t, which in this case is the total is 15 plus 1.5, 16.5 meters divided by 7 seconds, which should give you a value of 2.36 meters per second. We're going to end it here. Stay tuned for the next part, which is projectile motion. Hey guys, thanks for watching the video. If you find these really useful, then consider giving us a like and subscribing to our channel. For questions, leave them down below in the comment and we'll try to get back to you. For more academic resources, visit our website at NovaEdgeAcademics.com. We offer one-on-one tutoring service as well as college admission strategy. Let us know what you'd like us to cover next, and we'll see you in the next video.